Okay. So now in lesson 26 we will discuss modeling of AVRs. So last class or even a part of this class we discussed about the various controls of the power system. Okay. So what you have understood? Power system control. So when you say power system control, we are actually considering controlling of what? Two quantities only, frequency and voltage, because they correspond to real power and reactive power. The power, they are indicator of the real power and reactive power in the power system. Now the control system or the control loop that controls the frequency is known as automatic load frequency control, whereas the loop that controls the voltage is known as automatic voltage regulator. Correct? That we discussed. Till now we have understood that from one class. So, and I have told you this AVR loop is not very important because it is a electrical loop. It is very fast and with various control systems. Now this is not a problem at all. So voltage regulation happens, and also I have told you voltage regulation is generally a local phenomenon rather than a system-wide phenomenon. So it is controlled at the distribution level. Okay, no need of generator to always save the power system from low voltage. There are other means. Okay, so this is a small part of it, and we will devote only one class on this. Okay, but AFC, the frequency control can happen only by the generator, not by anyone else. Only the generator output can control the frequency of the whole system. Therefore, we will take two classes on this, which will be lesson 27 and 28. So what exactly we are going to do? We are going to develop control models, just like you have seen block diagram models. Okay, block diagram model. The whole purpose is to develop the block diagram models of these two systems, AVR and LFC. So LFC is larger, the primary one and the secondary loop. There are two loops, so we take two classes for that. Okay, and this will be only one class. We will have the overview of AVR loop. Then what we will do in the last two classes, in 29 and 30, in lesson 29 we will extend this power system control to a two area system. Now we will consider only one area, that means only one generator. There we will have two area systems, how they are connected, how the diagram, control diagram looks like, that we will see. And then last class we will see what exactly is meant by automatic generation control. Okay, how optimal dispatch will be integrated into the automatic load frequency control. Okay, so we will continue with the voltage regulators. So when we say AVR, what exactly we mean? AVR means, suppose this is a three-phase generator. It has a field system. Okay. In your lab, you are using some rheostat. In your lab, you are using some rheostat to control the field current and hence the flux or the voltage. In actual power plants, these are known as excitation systems. So this whole system is known as excitation system. Okay. So these are known as generator excitation systems. Okay. Now what we need, what power we need for excitation, field excitation, AC or DC? Alternator excitation by AC or DC? DC. Okay. So we need a, why DC, why not AC? Because from the very fundamentals of Faraday's law, voltage can be generated under three conditions. Okay, the first is when the flux is stationary and the conductors are moving. Right? The other one is a time varying flux, as in transformers. In transformers, the flux is time varying, whereas the conductors are stationary. Okay, two conditions. So either of the two conditions you have to use. Okay, in this case we are using the flux is stationary, that is DC. It's a DC flux, it's just available. Okay. Not that way, because in our case the conductors are stationary. You need the flux to cut the conductors. Okay. That flux cannot be time varying because you are rotating it, and hence it cannot be time varying. But in transformers, it is the flux is stationary. So as such, don't generate a voltage unless it is time varying. Okay, sinusoidal, unless it is AC. So in transformers, you have AC flux, whereas in machines, electrical machines, you have DC flux. Okay, field excitation is always DC. There is a third case also from Faraday's law, from electromagnetic theory. There is a third case where the flux is time varying and rotors are also moving. Okay, that is the third case, which is not applied in the situations. Okay, we won't go to the details. That is part of electromagnetic theory. Okay, part of GATE syllabus also. Okay, so here we need to supply DC. That's it. That means the whole purpose of excitation system is to provide DC to the field windings. So how can it provide that? The earlier oldest power plants used DC generators, simple DC generators. So you have got one DC excitation system, by means of DC generators. As simple as that. But now they are out of service. Not a single one is operating with DC now because of many problems associated with DC generators. Okay. So next came AC. Okay. AC excitation. AC excitation systems. But then we need DC. So these use rectifiers. Right? So they must use rectifiers. But then suppose you have a rotating AC machine. Any alternator, the stator is stationary, right? So it must remain on ground. Right? So you need to provide DC to a rotating field from another alternator where the stator is stationary. What is the meaning of AC excitation? DC excitation system is that the DC generator. No issues. You can directly provide DC to the system. Okay. But AC system, that means there is another AC generator. I mean, normal, the main AC generator is there, say 500 megawatt generator. But there is a small 1 megawatt generator which is providing DC excitation. But it is a AC machine. You need to rectify it. But in normal AC excitation systems, there is a problem connecting the rectifier output to the field windings because the field is rotating for the main machine. There are issues. Therefore, the modern AC excitation systems are known as rotating rectifier systems, or called, you might have heard this, brushless excitation systems. So everywhere you go to inductor plant, here captive plant, so they have all these brushless systems. So now currently only two systems are common. One is the brushless one, where the rectifier is rotating with the field. So no need of this all these mechanical arrangements. Okay. The other one is the simplest one. What is that? No need to provide any kind of generators. Simply take the some part of the output of the original generator and again give it to the field. Which will the generator. So what you do? You take the output from here itself, put a rectifier, give it to the field. Only a part of it. But then, in this case, what is the problem? Static crude acid. Right? You will find battery banks. Power plant, you have battery banks. For various purposes, they are there. But initial battery banks, it will start. Okay. But once it starts, so this kind of excitation systems are known as Nantivo. What are these called? These are called static excitation systems. Static. So these are called static excitation systems. Why static? Because in the first two systems, DC and AC, you have one additional generator, whether AC or DC, which is rotating. That's why those are not static. But in this case, there is no separate rotating excitation system. Only the main alternator is rotating. That's why these are known as static excitation systems. So three kinds of system: DC, which is obsolete; AC, there are two types. Normal AC is generally not used because of mechanical issues. Brushless is most commonly used, or the most common one nowadays are static ones. Okay, clear? Now we have to model. In this class we will model only the brushless one. Okay, static is still simpler. Okay, so we are going to model the brushless one. Okay, so as we discussed, the exciter is the main component of an AVR load. Which is the exciter? Either a DC generator or one AC generator, or directly output from the main generator. Okay, after activity. The basic role of AVR is on top of the exciter. Exciter is the source of the power, excitation power, whereas AVR is the control system, which signals the exciter how much power to provide. Okay. In older plants, the exciter consisted of a DC generator driven by a main generator shaft. Okay, I have told. So if you go to Uttarakhand, you might have heard J&K government is now planning to complete one power plant which was initiated in 1909, more than 100 years back. Somehow it was not complete. They are starting. So if you go to Uttarakhand, Jammu Kashmir, many old hydro plants, you will find out the old DC excitation systems which are out of service. Okay. Modern exciter, as I told you, modern exciters tend to be either static or brushless. Brushless meaning what? The rectifier is rotating with the main field. All of you know that in alternators, the armature is stationary, whereas field is rotating. In order to provide DC to the field, if you rotate the rectifier itself, no need of any brush and all these arrangements, no maintenance. Okay, therefore it is called brushless excitation system. Or static means direct negative output, the main generator. So we will go for the brushless system. Okay. So what exactly brushless system we have? So this diagram again directly I have taken from the elder book. Okay. You can find it many places. So here if you see, which one is our objective? Means this is the main generator. This is the main generator armature, which is on the ground, stationary. This is the main generator field. This is the main generator field. Whole purpose of the excitation system is to provide this field current so that the voltage is maintained. That's it. This whole arrangement on the back, the whole purpose is to provide this field current so that this voltage is maintained. Now this field current must be DC because this field requires DC. We need a DC excitation system. It's not transformer EMF. It's not time varying. Okay. So this field voltage is provided from a rectifier, which is rotating. And this rectifier is fed from another AC machine where the armature is rotating. Alternator general big size alternators, the armature is stationary. But in this particular case, the exciter alternator, that means the small capacity alternator, its armature is rotating and which is connected to the rectifier. Okay. And this is the exciter field, means the field of this additional small capacity alternator, okay, which is fed by means of this AVR. This is the AVR, Automatic Voltage Regulator, which is fed from this output signal by means of a potential transformer. Depending on the voltage here, this control system provides signal to the excitation of the exciter, the small capacity alternator, which either increases or decreases the field. Okay, that's it. So in order to model this control system, you need to model the alternator, the exciter, and the AVR. Right? So we start with exciter modeling. How to model the exciter? You can go through the details later. Okay. What is the meaning of a control model? It's a transfer function. Okay. The output of the exciter is DC. The output of the exciter is DC. Output rectifier. So this is actually amplifier output. Okay. Amplifier output. And this is the error signal. So based on the error signal, one voltage will be given to the exciter of the rectifier. Okay. And all these details are here. Okay. And finally, this is the transfer function of the exciter. GE means transfer function of the exciter. And what are the other things? GA means transfer function of the amplifier. Why you need an amplifier? Because the voltage that will be generated based on the error signal will be very less. You need to amplify it. So finally we get this model. Okay. Draw this with each group cap. Okay. Or we can draw in the next slide where other things should be combined. Okay. So what exactly you are going to do? You find the exciter model, which is this one. Okay, exciter model. This is the amplifier model, and this is the comparator, which is comparing the actual voltage with the required voltage, reference voltage. Okay. So this one is, what is this? This one is the field voltage of the main alternator. So what part is missing here in this model? Which one? What part is missing here in this model? Feedback path is this one. Comparator is the feedback path. Amplifier is the output of that error signal. KE is the exciter gain. That means which is providing field supply to the main alternator. So the main alternator is missing. Right? We need to model the main alternator. Okay. So then when you generator modeling is modeling of the main generator. Okay. So this is the typical area code. Okay. So you have got this generator field, exciter field, amplifier, and comparator, and each have different time constants. Exciter time constant, amplifier time constant. As I have told you, these are all very fast in terms of milliseconds because this is a complete electrical system. No mechanical thing is involved here. Then using what will be GS? GS will be GA into GE into G generator. Right? It will be a multiplication of that. Then using this feedback loop, we will find out the total transfer function of the whole excitation system. Okay? Fine. Then we find out the static performance of the air slip. What is the static performance of a control system? Static means what is the final error? Suppose the input is unit step. So finally you need to reach 1. So what is the final error? How far it has succeeded in reaching that 1? Okay? So that is known as error or the static response. Okay, that you find out by limit t tends to infinite, t in time domain, or limit s tends to 0 in s domain. Right? So here it has been done. Okay. Okay. Then dynamic response. Dynamic response means how fast it reaches there. That is dynamic response. Go through it. Okay. Now one example is there. One question I have given in the problem set. You can see that. From there we get this transfer function, and if you plot in some any software, MATLAB or Octet, you can find out this curve like this. Okay, so this part is the dynamic response, whereas this part corresponding to the original output will be the static response. So this completes the AVR. Next, the remaining 4 classes will focus on AVRs.